Hello folks, here we are for our second in the series of lectures from a meteorological standpoint on Skew-T log P diagrams. And so again, we're jumping into our top hat 602987 for Adam's class, 393390 for Kevin's if you've put this aside for a little while. And so we're here on page 6 of the handout, part 3, and trying to delineate some information from the Skew-T. Lots of lines, and now we're drawing some additional lines of temperature and dew point as we move up in the atmosphere from our radiosonde, our instrumented balloons that we launch up. And so now we're going to talk a little bit about this idea of generating a parcel path and some of the derived values that we can achieve. And so the first thing we're going to focus on here is the lifting condensation level, usually referred to as the LCL. And so this is the first critical step that we need to do in order to be able to draw our parcel path, or how our parcel, this fictitious blob, is going to rise in the atmosphere. Because if you recall back to Met 103, we're oftentimes, or I should say, we are going to be concerned with how our parcel is relative to our environment in terms of temperature. Remembering that our warm parcel, if warmer than the environment, will want to rise, and if our parcel is cooler than the environment, it will want to sink. This idea of density within the parcels. And so here, finding the LCL is actually very simplistic. We have to take our surface temperature and our surface dew point. Mind you, there are some occasions, and some of the examples that I show you here soon will illustrate this, where you may have some really intense surface heating, maybe potentially a small issue that occurs with a balloon that may cause some really sharp changes in the lowest couple feet of the atmosphere. And so we want to be a little careful of that. And so sometimes averages may be used in the lowest levels of the atmosphere. But here we're simply going to take our surface dew point and draw a line upward along a saturation mixing ratio line. We may have to interpolate between different lines because rarely are things going to fall exactly on any of these lines in our thermodynamic diagram. And at the same time, we're going to take our surface temperature and we're going to look at the dry adiabatic line, the one that moves from the lower right towards the upper left. And the point at which this fictitious line, or this sketch that we make on the dry adiabat and then the other one on the saturating mixing ratio line, where these two intersect is going to be known as our lifting condensation level. The idea that as we lift this parcel dry adiabatically until the point that it becomes saturated, and this is where condensation would occur if we were to actually lift this parcel up. Remembering that there are many ways that we can lift a parcel. And so this is going to be one of the things that you spend a little more time on in your curriculum next year. And there's other levels, such as the CCL, or the convective condensation level. And so this, as I said already, is the first step in order to be able to draw our parcel path. And this is a larger size diagram in terms of looking at a greater depth of the atmosphere. And you can see towards the bottom portion of this image, we've already sketched out our lifted condensation level. And so at this point, we change the way in which our parcel is going to rise. Until we hit the LCL, it's cooling at a rate at 9.8 degrees Celsius per kilometer, that dry adiabatic lapse rate. However, moving upward from this point, we're going to shift to the moist adiabat line. Again, it's unlikely that your sketch for whatever's going on in the atmosphere on a given day is going to fall perfectly on one of these moist adiabatic lines, and so we're simply going to parallel surrounding lines. This takes a little bit of skill because of all of the different lines that are on a Skew-T log P diagram, but with practice will become easier. And so here we simply take this parcel, raise it to the LCL, and then we start to simply follow the moist adiabat higher and higher in the atmosphere. And so there's going to be a couple of points at which we are quite interested of this intersection between our parcel and the environmental temperature. And so this diagram is signified by this solid black line, our dashed line being that dew point profile as we ascend to the atmosphere. And so here we can see from the LCL up through the LFC, we have a parcel path that is to the left of our temperature profile, the environmental temperature. And so the LFC, the level of free convection, is kind of what it sounds like, a level at which convection will occur freely, convection being this rising motion that we're going to experience in the atmosphere. So as we find the LCL and follow that moist adiabatic line upward, when it intersects the temperature sounding becomes the LFC. And you can already see, and we'll talk about this shortly, this idea of a negative area which the parcel is cooler than the environment. It's not going to want to rise unassisted within this level, or this, I should say, vertical depth of the atmosphere. The next line we're interested in is continuing to rise our parcel path along this moist adiabatic line. When does it then intersect the temperature profile of the environment again? This point is known as the equilibrium level. And so for the layer in between the level of free convection and your equilibrium level is this positive area, an area in which your parcel temperature is warmer than the environmental temperature and therefore will want to rise unassisted. And so this positive area is going to become very important when we talk about a parameter not long from now called convective available potential energy. And so a lot of what's going on here is simply what we did back in MET 103, but now we're using a technical diagram to get some greater detail with regard to various levels of the atmosphere, with understanding actually how much warmer than the environment the parcel might be. And so we can take a lot more from one of these Skew-T log P diagrams than the simple basic stuff we did back in MET 103. And so quickly we're going to look at and think about some of the parcel paths in a couple of actual Skew-T or some sounding data. And so this would be one from many years ago, 2012, near Dallas, Fort Worth, Texas. And so you can see as we look down here by the surface, really near saturated temperature dew point spread near the surface. We are effectively saturated, not far here above the surface. And then we have some separation, temperature warmer than the dew point, near saturation before we have a significant dry layer here above 500 millibars. But a couple of things you can see here is that in this example, our LCL would be very low to the surface. We would have this dry adiabatic trace upward. We would then also be following our mixing ratio line, and so we have an LCL very low to the surface. Upon hitting this LCL, we would then rise along our moist adiabat upward. We would have some negative area, likely here in this 850 to 700 millibar layer, before we would emerge and have a very deep positive area from anywhere somewhere around 700 millibars up to probably somewhere a little bit above 200 millibars, where we would then hit the equilibrium level. And so remembering, this first one is going to be called the LFC, the level of free convection, until it recrosses at the equilibrium level. And so you would end up drawing a very large positive area within this diagram. And so this would be an example of a Skew-T, or a sounding that would be conducive towards severe weather. Another very interesting thing to point out with this sounding is the wind profile. Look at your surface winds. We have winds from the south. Let's see if it comes back in here. Not sure why it kind of blipped out there a little bit. Oh well, the breaks of the game when it comes to actually trying to do these things on a video. You see some southeasterly winds transitioning to southerly winds, and then to southwesterly winds with a sharp increase in speed. So we have both speed shear as well as directional shear, and this would be an example of that veering profile that we talk about in the atmosphere. Again, conducive towards warm air advection and also severe weather development. This is a Skew-T from Valparaiso University. We usually will refer to our Skew-Ts, we'll give them the identifier of VUM for Valparaiso University Meteorology. This would have been taken in 2012 on Leap Day, and this would be at 18 UTC. And so you can see a pretty sharp delineation between your temperature and the dew point. But again, this is an example of we may want to be really cautious down here by the surface. Probably didn't cool off that rapidly. It also probably didn't necessarily dry off that much within a small layer above the atmosphere. It's things that we simply need to be cautious of. And so in this example, we can, if say we take this as the surface dew point, and this is the surface temperature, we rise this up along the dry adiabat, we raise this one up along our dashed blue lines, and we would end up with an LCL a pretty far distance here above the surface, upwards of 850 millibars, but below 700 millibars. And then if we simply trace that along a moist adiabat, you would see that the majority of our sounding here would be to the left of the environmental temperature, and this would not be a setup conducive towards convective type clouds. If you look at our wind profile, you'll notice it's much more unidirectional in nature. Generally, southwest to west-southwest winds the entire way up, but we do have some strong winds as you go higher in the atmosphere, pushing upwards of 115, 120 knots around 300 millibars. Now, if we take a look for one more moment at this image, and we toggle forward, this next image is going to be from a few hours later. And so I'll toggle back and forth a couple times. 18 UTC, 22 UTC, 18, 22. And so you'll note that we've, in this relatively short amount of time, really saturated some of these low to mid levels of the atmosphere. We would still have, if we assume this to be the surface dew point and this to be the surface temperature, we would still have an LCL relatively low in the atmosphere, but even maybe a little bit of positive area within this setup. And so more than likely we would see some clouds here due to this level that is near saturation. And it's an interesting setup in terms of what might be expected as we evolve throughout the day. We do take our regular balloon observations at 12 UTC and 0 UTC at stations across the United States. Sometimes they get supplemented by additional data, especially when severe weather is possible. And so we'll end this lecture talking a little bit about stability indices and actually look at a little bit what's going on today, this being taken on Thursday, the 9th of April. And so we can look at some snapshots, values that are going to give us an idea of the stability or instability of the atmosphere, but we must be cautious because there are many, many ways in which we can look at the stability of the atmosphere. Some of them are going to look at stability over a greater depth of the atmosphere, while others are going to look at them within a single layer. And so we have to be cognizant at all times of what exactly are we looking at, and never to simply take one parameter as the entire story about what the atmospheric state is. And so lifted index is one starting to get to be a little less used, but it's still available on many websites, including the Storm Prediction Center, way of looking at atmospheric stability, focusing on the 500 millibar layer. And so here the Li is simply taken as the environmental temperature at 500 millibars and subtracting off the parcel temperature at 500 millibars. And so if this value is positive, meaning the environment is warmer than the parcel, we know that that is a stable scenario. Parcels warmer than the environment want to rise, and so in this example, if our parcel is cooler than the environment, resulting in a positive Li, it's going to mean that this is not an unstable situation, and we would not expect to see severe weather with positive values of lifted index. Conversely, if this value gets less and less than 0, meaning this parcel is substantially warmer than the environment at 500 millibars, we're going to become more and more unstable. And so there's a chart, or I should say a table within your handout that gives you an idea, especially as we start seeing LIs -4, -6, -10, -12. It's showing that that parcel, we have a much larger positive area in the mid-levels of our atmosphere. But the thing that we need to be cautious of with lifted index is it is simply looking at one layer of the atmosphere. This is a major drawback. Li was widely used a couple of decades ago, but is something that we look at now as meteorologists, but always in conjunction with other stability parameters to diagnose the atmosphere. One of these parameters, and one that you have likely at a minimum heard of, is CAPE, or convective available potential energy. Harkening back to a few slides ago, CAPE is going to be this positive area on the Skew-T, the area between your LFC and your equilibrium level. And so you see a little bit of calculus type stuff here. We have an integrated quantity from your LFC to the equilibrium level based upon the change in pressure. And this is going again to look at this integrated quantity, our R being an ideal gas constant. And these are going to be temperatures of the parcel at various levels as well, looking again both at the environmental temperature as well as the parcel temperature. And so the larger that positive area on a Skew-T, the larger your cape. There are a lot of different ways to analyze cape. And so if you find this to be something you're very interested in, I encourage you to not get overwhelmed, but take a gander at some of the products on the Storm Prediction Center webpage. Look at the mesoanalysis. Look at the thermodynamic information. You'll see features such as SB cape, surface-based cape, ML cape, or mixed layer cape, and MU cape, or most unstable cape. You shouldn't expect to understand all the underpinnings of these different types of cape, but realize that there are many, many ways that we can dissect the atmosphere in order to best forecast the potential for severe weather events. When we look at cape, we're looking for values primarily over 1,000 joules per kilogram. This is going to be the unit of cape, and this is going to be as we get greater and greater values of cape, meaning more and more instability. However, be cautious. Not always is extreme instability or 5, 6, 7,000 joules of cape going to be conducive to severe weather. It likely indicates that we have a very staunch cap. Harkening back to the negative area, this would be what is known as CIN, C-I-N, or convective inhibition. In order to get extreme values of cape, we are also likely going to have to work through some significant CIN in order to, quote, overcome the cap. None of you were alive, but in the great Chicago heat wave of 1995, I would encourage you, if you're sitting around with not a lot to do, to read up a little bit on it. It was fascinating. If you are familiar with Chicagoland, I'm pretty sure Naperville had heat indices up to 127 degrees Fahrenheit. But in this example, we had cape values around 8,000 joules per kilogram, but nary a cloud in the sky. And that was because there was simply so much convective inhibition that any upward motion was going to be stymied by this negative area. And so, we're going to take one more moment here and look at what's going on a little bit in the atmosphere today. And so here's our day one outlook. We can look a little bit down there, focus on that Austin, San Antonio, Houston area with an enhanced risk. We see a relatively minimal tornado risk, 30% wind, and 30% hatched hail. And if you're sitting here thinking, what the heck is he talking about? Notice how here it talks about some of the values with probabilities and hatching and more information. So if this is something you find interesting, again, peruse. It will get you in better shape for that MET 216 and MET 279 curriculum next year. So if we take a look at the mesoanalysis, we can look again here at the thermodynamic breakdown, and we click on CAPE, surface base. Notice other ones here, that MU CAPE, normalized CAPE, downdraft CAPE. Oh my gosh, there's a lot of CAPEs. But let's look at surface base for now. And you can see that ahead of where we have some thunderstorms and within this enhanced risk region, we have some very high CAPEs. 6,000, 6,500 areas. And this is going to be one of the main reasons we are expecting to see large hail upwards of 2 inches in diameter later today as these storms get better developed into the afternoon hours. We can also look here at the surface base lifted index. Again, our difference between our parcel temperature at 500 and our environmental temperature at 500. And here we see negative values, negative 10, negative 9, negative 8, large negative values. And these are going to be where the parcel temperature is significantly warmer than your environmental temperature, and therefore we have a lot of rising motion in that area of the atmosphere. And so we'll conclude by briefly looking at an example model Skew-T. This would be for an area probably not too far away from San Antonio, Texas. And so we can see here where we would have an LCL and an LFC pretty close to one another. See our CAPE, 4,000 joules per kilogram. with a convective inhibition or negative area approximately 0. So this is suggesting in the model that by 21 UTC we likely are going to have convection breaking out. And since what we just looked at, it's about 20 UTC as I'm putting this together, we already saw some convection that is popping up across portions of Texas. Lifted indices -11. And so we can see a lot of the parameters here through this Skew-T that are going to again be conducive with this really large positive area at our equilibrium level here where our parcel path crosses back over our environmental temperature. So this entire area here, if we were to integrate it and color it in, this would be our cape. We effectively have no cap. But the one thing, the reason we don't see a great threat for tornadoes is our shear. We have some directional shear, but notice the wind speeds. They're not very strong until you get up here around 300 millibars. And so because of this lack of speed shear, they're not expecting a very significant outbreak of tornadoes on a day like today. That concludes our lecture here on some of the initial parameters, drawing parcel paths, and understanding how to analyze Skew-Ts. I hope these videos are helpful, and I encourage you to dig deeper as you feel appropriate in these types of scenarios as our spring continues to produce days with severe weather. Have a good one.